And welcome to this week's COVID-19 and MS call. For those of you who are new to the call, we have been holding these calls weekly, and really the aim is to provide a platform for clinicians and scientists to exchange their experience and as we are learning on the go, to really provide the best care for our patients and also scientifically learn more about how COVID-19 acts in MS patients. So I'm excited to see so many known and also new faces on today's call, and I'm specifically excited that we have 4 lady speakers this call. We're going to start with Sandra Amor, who's going to give us an update on innate immune evasion in COVID-19 patients, and then we'll have people from 3 international registries share their experience. It'll be Celine Louapre from France. We'll have Afagh Garjani, and please apologize if I'm not pronouncing your name correct, from the UK team presenting an update. And as a third representative from Registries, we'll have Amber Salter representing the US and Canada, share the experience of COViMS Registry. Before we start, just a couple of technical notes. First of all, this call, as every call, is being recorded and made publicly available on our webpage after the session. So please feel free to share the information with colleagues who didn't have time to join. In terms of questions, we should have enough time to take questions right after the call. I also invite you to make use of the chat function. You find that on the bottom of the Zoom, and you can also post questions as we go, and I'll keep an eye out for those. And I'll make sure to have time in the end to have a couple of minutes to wrap up and have another discussion. And we'll now go ahead and mute everybody to reduce background noise. So please make sure to unmute yourself if you want to ask a question. And I'm inviting our first speaker, Sandra Amor, to share your screen. Sandra, we will look forward to your presentation.
Okay. I'm trying to do this. Okay, I hope everybody can see this.
Yes, perfect. The screen is shared.
Okay, so I'm going to talk a little bit about innate immune evasion and also discuss some of the strategies that maybe SARS-CoV-2 uses when triggering the innate immune response. So I'm going to move this that way. Okay, so I guess most of you have seen this before about the genome structure, the genome, and also the structural and the non-structural and the accessory proteins. So here's my take on the virus itself. So throughout the presentation, I've used a blue to denote the spike protein, yellow for the nucleocapsid protein, orange for the membrane, green for the membrane protein, and orange for the envelope protein. So I guess most of you know this, but I'm going to go over it. The genome is translated forming these 2 large polyproteins, PP1A and PP1AB. This is due to frame shifts in during the translation. So this is the ORF1A and the ORF1B. So this is the 5' end and the 3' end. The non-structural, or the proteins are, there are 2 non-structural proteins or viral proteases that actually break down these long polypeptides to form 16 non-structural proteins. So this is what the ORF1A and the ORF1AB do. At the 3' end, there's the spike protein, the envelope protein, the membrane protein, and the nucleocapsid protein. So this is coded at the 3' end, along with a number of accessory proteins. Now, I've done the accessory proteins in dark pink. So these are the ones that are definitely known for SARS-CoV-2. So this is 3A, 6, 7A, 7B, and 8. There is some discrepancy about 3B, 7B, 9A, 9B, and 10, because some people don't actually see these accessory proteins when they're looking at when they're investigating the SARS-CoV-2. So, so what we have is the non-structural proteins, the structural proteins, and the accessory proteins. Now, both 3AB and also 8 differ from SARS-CoV-1. So if you read anything about the role of these accessory proteins, they're different from SARS-CoV-1. Oh, no, I can't seem to, oh, okay. So if we're looking at the infection and immune response, we think, I think what I think is there's a balance between the rate of infection, the viral dose, and also the immune response, and all these three factors determine the outcome of the disease. So if we look at some of these factors, and I'm not going to go into all of them today, but there's the interferon response, the antibody levels, the CD8, the lymphopenia, ROS production, and the role of immunosenescence and also TLR signaling. And this is balanced by the viral load, the viral spread, how much the virus induces immune subversion or immune suppression, and also the extent of the tissue damage and the damp-induced immune response. So generally what we think is that an early burst of the type 1 interferon response leads to detection. However, a delay in the interferon response enhances the virus replication and also the cell damage. And this increases the DAMPs, these danger-associated molecular patterns, also the innate immune activation, and all these contribute to the inflammatory cytokine storm. And this likely predominates in older individuals, as shown also in the aged mouse models of SARS-CoV-1 infection. So what I'm going to tell you about today is about how the virus uses its glycosylation pattern to evade the immune response, how the replication also avoids the pattern recognition receptors, how the virus has developed a form of RNA shielding, so to prevent innate immune activation, and also how it inhibits the interferon signaling, how it can activate the macrophages in a specific way, the role of complement, and also the renin-angiotensin system, and the impact on the neutrophils, ROS production, and eventually thrombosis. So if we look at glycosylation, many viruses exploit the host cell machinery to glycosylate their viral proteins. And for SARS-CoV-1, at least, we know that polymorphisms in the C-type lectins, the ones that recognize the glycosylation, the glycans, can actually predispose to having more severe disease. The virus also uses DC sign as a co-receptor, and this facilitates the entry and transport of SARS-CoV-1. And we think that it also, or there is some evidence that maybe this also operates in SARS-CoV-2 as well. And we know that mannose binding lectin, so MBL, that's in the plasma, can bind and inhibit the SARS spike protein mediated viral infection. And this also blocks the C-type lectin interaction. So I found this very nice picture by Grant here of the glycosylation of the SARS-CoV-2 protein. And for each of these protein spikes, if you remember that it's formed of 3 spikes. So for each individual spike, there are 22 glycosylation sites per spike. So that's 66 per, let's say, spike of formation, so to speak. And also the receptor binding domain is glycosylated. And so if we're going to develop a neutralizing antibody, this also has to take these glycans into account. So there was a paper by Watanabe in 2009. So SARS-CoV-2 is actually not on this graph, but as I understand it, SARS-CoV-2, so this is the glycan shield density. SARS-CoV-2 is much higher than the other coronaviruses. So these are the coronaviruses, and this is HIV and SIV, for example. And this is the percentage of glycosylation units, or let's say glycosylation measurement per virus. So you can see that some of the viruses actually have a very large glycan shield density. And this also goes for the SARS-CoV-2. So if we look at what the role of glycosylation might be, this was another paper by Watanabe in 2019. So they showed that glycosylation can help the virus evade the immune response in a number of ways. And here they gave the example of HIV and dengue and also Ebola. It can also aid as molecular mimicry, so therefore evading the immune response by mimicry, blocking the antibody response. The glycosylation or the glycans can also aid uptake by either the host cell or the target cell, so it's recognized by maybe the T cells or the B cells or antibody. It can also activate the innate immune response and activate complement, as well as be recognized by antibodies, so antibody epitopes. So for SARS-CoV-2, the glycans we know can mask the immunogenic peptides, bind via DC sign, as well as activate the complement system. So obviously SARS-CoV-2 was not known when Watanabe published this paper, but we certainly know that SARS-CoV-2 can be added to a number of these factors where we know that glycosylation is involved in the virus infection. So this might be very complicated, but this is my take on how the virus can actually evade the pattern recognition receptors. So if we look at the virus binding, fusing, and entering the cell, the genome is translated, and we have at the 5' end, the genome is capped, and I'll tell you about that in the next slide. But by capping the RNA, the virus actually evades recognition by some of the innate receptors. Then there is the replication stage, which takes place on these so-called double membrane vesicles. And in fact, all this here, all this replication steps here, takes place in these double membrane vesicles. And I think I have a picture here. So somebody had done some scanning EM, showing that this is what these double membrane vesicles look like, this replication complex, and everything takes place within these double membranes. So the replication, actually the replication takes place behind, let's say, a barrier, so that the innate immune response within the cell does not recognize the viral RNA, and in fact even the subgenomic messenger RNAs, and also some of the proteins when they're translated. The virus is then assembled via the ER and the ERGIC, which is the ER-Golgi immune complex, or complex, I should say. And then the virus buds, forms its envelope protein, and then is released from the cell. So here there are two major steps where the virus actually evades the innate immune response of the host cell. So if we look at how the virus actually shields the RNA, I've told you that the RNA and the protein production takes place behind these so-called double membrane vesicles. But SARS-CoV-1 and also SARS-CoV-2, the RNA mimics the host RNA. So this is a capped host RNA. This is the capped SARS-CoV RNA. And the two innate receptors, so the MDA5 and also the RIG1, will recognize either non-capped RNA or even incomplete or methylated caps and double-stranded RNA. So these are recognized as pathogen associated molecular patterns, so will activate the innate immune response. So viruses, and particularly coronaviruses, hijack the cellular capping mechanism, or they can actually snatch the host cell messenger RNA caps, or indeed encode capping enzymes. And this is how the SARS-CoV-2, the RNA is shielded from the innate immune response. And for the SARS-CoV-1, and we think also for the SARS-CoV-2, both the non-structural proteins 10 and 16 actually aid this capping system, very similar to the host RNA, so thereby avoiding the innate immune recognition. So the next step is how the virus evades the immune response is actually by inhibiting the interferon signaling pathways. So I'm not going to go into very much detail here because it's quite complicated, but by activating the mitochondrial antiviral signaling, the yeah, to cut a long story short, this activation pathway can activate the interferon signaling. So I'm just going to show you how the non-structural proteins can interfere or contribute to this so-called inhibiting the interferon signaling. First of all, the non-structural proteins 13 and 16 aid the capping of the RNA. We also know that the nucleocapsid protein and also the membrane protein, when it's translated, can interfere with NF-kappa B signaling, but also for the nucleocapsid can interfere with this pathway signaling here. Now, I don't have so much time to go into all the details, but I've put in all the different non-structural proteins and also some of the ORF proteins. So you can see that when the virus is replicating, it has a number of different systems to actually block the interferon signaling. Now, we all know that macrophages are involved in the SARS-CoV-2, in the cytokine storm. And there's been a lot of controversy over whether the virus, what the virus does when it actually infects the macrophages. So it doesn't produce a productive infection, as in it doesn't produce live virions, but we do know that it does infect the macrophages and again suppresses the interferon response in some cases. So this was a study, I haven't put the reference on here, but this was a study using DCs and also a macrophage cell line which were infected with the SARS-CoV-1, and you can see that in this case, even infecting the DCs suppresses the interferon alpha response. Now, the ORF3A can induce necrotic death, as we've seen in the lungs of people, but also in other organs. And this produces oxidized cell debris that can activate TLR4, and this has been shown for SARS-CoV-1. The virus also can bind to macrophages through DC sign or CD147, or indeed through the ACE receptor major, and activate the TLR pathway. So to cut a long story short, the infection of macrophages, although it doesn't produce productive virus, it does interfere with the signaling and mainly activates the inflammasome. So this is what activates the, contributes to the cytokine storm. So complement, if we look at complement, we know that complement deposits are also seen in the lungs of people with COVID-19. But if we look at the virus, as I said, it's glycosylated. There's a protein called mannose binding protein that's in the plasma that can bind to the glycosylation sites, and this can activate the lectin pathway of the complement system. But the virus is also known to activate the classical pathway by binding to C1q. And this will activate complement, of course, but also recruit inflammation and contribute to the cytokine storm. So we know that the role of complement may be quite important, basically from the mouse studies where people have used the C3 knockout mice. And while these mice had a similar viral load as wild-type mice, they developed less severe disease, fewer neutrophils, and also less activated macrophages. So we know that complement can actually play a part in the pathology of COVID-19. So you've probably all seen this before, but this is my take on, to cut a long story short, this is the virus. The virus will bind to the ACE2 receptor. And when this happens, it tends to push the system, the renin-angiotensin system, into a balance where we have more increased oxidative stress. In this way, and also it prevents the protective side. And when we have increased oxidative stress, this will attract neutrophils, so neutrophils and activated macrophages that contribute to the ROS production. This will activate the endothelium. But we also know that the nucleic capsid, or there have also been some studies showing that the nucleic capsid can also activate the coagulation pathway. Now, most people have been thinking that maybe this actually activates on the endothelium, but a recent paper has actually shown that, at least in mice, where they have used knockout studies, that actually this impact of ROS is actually via parasites, which also influence the von Willebrand factor and activates the coagulation pathway. So this is my last slide now, and if I had to hazard a guess as to what the difference was between people that have asymptomatic or the ones that actually have a more severe disease, it's basically would be the viral load. So if you have a low viral load, there will be minimal interferon blockage with little cell damage, and the virus will be cleared. If you have a high viral load, there will be a disbalance in the RAS, and this would push pro-inflammation. You would also have interferon inhibition, which would be much greater, and this would lead to an increase in viral titers, an increase in macrophage infiltration, an increase in cell damage, which would then activate DAMPs. Also, you would have increase of neutrophils and macrophage activation, which contributes to the cytokine storm. Now, there have been several papers that also show that activation of DAMPs and also higher interferon can actually decrease NK cells. So that would actually contribute to increased viral load, and the increased ROS production would contribute to the vascular damage. And that was my little presentation for today. So thank you for listening.
Thank you very much for this very comprehensive and very clear overview of how SARS-CoV impacts the innate immune response. Are there questions from the audience? I see one in the chat, so I'll start out with this. So the question is from Margaret Burnett. Do you know if higher interferon at the time of infection may be an advantage?
I think that's from what I've read. Yes, definitely, and definitely in the mouse studies that yeah, if you have higher interferon responses, then you're more likely to be protected. Yes.
Great. Are there other questions?
Yeah, I have one. Tony Reeder. This might be a little technical, but I saw in one of your things that the CLEC4M protein was a co-receptor.
I'm sorry? Sorry, I didn't get the question.
The CLEC4M protein was a co-receptor.
Oh yeah, the select. Yeah.
Okay, so I just looked at, I don't have a signal for CLEC4M, but the A, B, and C are up in untreated MS, and D and E are induced by interferon therapy. And
okay.
So how are they related to M?
Oh, I have no idea, actually. I could probably look it up. I'm going to write it. I've written it down, so I'm going to look it up. Yeah, sorry, no, yeah, I'm not. I don't know. Yeah.
So A, B, and C are up in untreated, and D and E after an interferon dose.
Okay.
Okay.
Sorry, I can't answer your question.
I know.
Thank you.
I thought your talk was great, by the way. Okay.
Thank you. So we have a question from Georgina from Spain. She asked if the type of interferon also influences the response to the virus.
When you say the type of interferon, whether it's, you mean type 1, 2, or 3, or is that what you mean?
I assume so, yeah. Mm-hmm. Yeah.
Well, I don't know very much about type 2, but certainly with type 1 and type 3, those are the ones that people have been looking at for the antiviral responses, definitely.
Great, thank you. And on that note of interferon, Hal Tremler just posted in the chat. I'm just looking it up, but apparently there was an editorial in Lancet last week that relates to interferon beta 1b for COVID-19. So you may want to check that out.
I will.
I also have a question for you, Sandra. I mean, there has been a lot of discussion in terms of how children are fairly protected and then how adults are not, and a discussion about immunosenescence. How do you see that? You know, is anything known from an innate immune perspective? I know there are a lot of discussion how adaptive immunity would be different.
Yeah, sure. I think from the innate immune response, it's probably acting in the same way. Definitely, if you look at, say, microglia, I mean, I haven't done very much about macrophages, but I have looked at microglia, and certainly with microglia, they take on a more activated form during in senescence. So perhaps if it's the same with macrophages, maybe they produce more, they're going to be more susceptible to actually inducing the cytokine storm in older people.
Thank you. I don't know, maybe Helen, I don't see you right now, but do you want to quickly comment on the editorial? Well, maybe we'll keep this to wrap up the talk in the end. So if there are no further urgent questions, then we'll keep them for the end. And I'll thank you again, Sandra, for this really nice overview. And we are moving to our next speaker. We'll go now to the registry, and we'll have Celine Louapre present, representing France. Celine?
Hello, everyone. Yes. Do you hear me?
Yes.
Okay. So maybe just before we start with the registry, I just maybe wanted to give you an update of what's happening in France now. So we are arriving at a clear decrease in the number of infections and deaths linked to COVID-19. The deconfinement, I don't know if there's a word for that, started a little over 2 weeks ago. And at the beginning, people were very careful the first few days. Now we feel that the recommendations are starting to fade a little bit. The cafeterias have been open for 2 days now, and there seems to be some people gathering in Paris and around. So at the hospital, the precautions are measure remain fairly strict. I think it's the same everywhere now. On-site consultations concern only a third of the patients about, and for the day hospital, we still adapt the schedules to limit the contact between the patients. So everything is changing quite quickly, but it's going to the right direction. So now I just wanted to update you on the French registry, the COViMS Registry. So currently we have a little bit, almost 350 patients with MS, 11 patients with NMO disease. So this will be an update of data that we presented a few weeks ago. Most of the patients are relapsing remitting patients with a median EDSS of 2.0. This is the comorbidities of the patients, and the diagnosis has been done either through a PCR swab or thoracic CT or typical symptoms. Maybe I should put that in full screen. So this is the severity of the COVID that we are representing according to a scale from 1 to 7. 1 is not hospitalized, no limitation on activities, and 7 is death from COVID-19. And here we present the data only about the patients with MS. So we have 73 patients who had a COVID-19 severity score over 3, which means at least hospitalized, and 12 patients of the cohort who died from COVID-19, which is 3.5%. It could be considered not that different from the general population, but the thing is that this population is younger than the mean population, general population. So if we really try to compare with what is happening in patients with a mean age of 44, we are certainly a little bit over the death rate that would be expected in that population. And here in the bar graph with the blue colors, so you have the severity score with the different shades of blue. So dark blue is the score 7, so death. And what we observed in this cohort is that the patients who had the worst outcome were the one in the untreated group. These are also the patients who were slightly older and with a higher disability compared to the treated patients. So then we run a univariate and multivariate analysis about the risk factors of having a severe COVID-19, so at least hospitalized. And when we did this analysis, so it was a multivariate logistic regression model to determine which are the risk factor of having at least hospitalization or death from COVID-19. And we used a stepwise selection method. So treatment was not retained in the model. And the variables that were retained were age, obesity, cardiac comorbidity, although not completely significant, and EDSS. And EDSS had the highest impact on the outcome, which was a clinical score over 3. And just because this is something that was previously discussed also, we ran another logistic regression model with the same outcome, at least severity of 3. And with a stratification of the treatments with no treatment, treatment other than anti-CD20 and anti-CD20 treatments, and other covariates that we wanted to include in the model, such as progressive MS, EDSS, of course. So EDSS here is presented by 1 point of EDSS, 1 point of EDSS increase. Age is plus 10 years increase, and we did not find a difference, even taking into account all the other variables, between the untreated patients and the patients treated with anti-CD20, and the patients who were on other treatments did not have a significant odds ratio of having a clinical severity score over 3. So I think that was the last slide from this update for the French registry.
Thanks a lot for Celine for this very nice update. Are there questions?
So my question is about interferon. Do we have the impression that maybe there's more patients on interferon that may be in the lower severity category?
Yes, that's a very good question. And also we were really struck by the fact that none of the patients that were reported treated on interferon, none of them has been hospitalized. So we don't have so many large number for each category of patients. So that's why this can be maybe investigated with larger cohorts or with combining different cohorts. But at least in France, none of the patients on interferon were having a severe disease. So interesting. I'm sorry, we have a storm in Paris currently.
Celine, could you comment, and I might have missed it, but you saw a higher mortality rate in the untreated patients. Do you think, or do you have data support that this is driven by them having a higher EDSS or
Yes.
being obese,
yes.
or having higher morbidity because of not being treated?
No, that was driven by higher EDSS. And also maybe they were slightly older, but this was really EDSS which was driving this trend to a higher severity.
Mm-hmm. And I believe this is also being seen by others. I mean, we'll hear from 2 other registries, but I've seen it. So, yeah. Are there other questions? Well, then we'll keep questions that are coming up for the end, and we'll move to the next speaker. We now have Afagh from the United Kingdom presenting an update on their registry.
Hello, thank you for having me. I'm going to present an update on the findings of the COVID-19 and MS study, which is part of the UK MS Register. I'm presenting the findings on behalf of Nikos and Richard, which are leading the study, and the rest of the research team. So here is an outline of the COVID-19 study flow. On 17th of March, when the study was launched, we emailed people with MS who were already registered with the UK MS Register to take part in the COVID-19 study. These were 18,000 people. However, among them, only 3,500 had been actively taking part in other studies of the register within the past 6 months. We also advertised the study, and by the end of 24th of April, we've got 3,500 people with MS on the register joining the COVID-19 study, and an additional 500 people with MS joining the register and the study as a result of advertising the study. So that gave us approximately 4,000 people with MS responding to our first survey. And we asked people if they thought they had COVID-19 or not. And 237 people with MS reported a self-diagnosis of COVID-19. And similar to other studies, we believe that a self-diagnosis of COVID-19 at this stage of the pandemic is probably the best practical and useful way of detecting COVID-19 cases as compared to only relying on PCR testing or healthcare professional diagnosed one. So that gave us an incidence of 6.1% of COVID-19 among people with MS. And here are a few numbers. 37 also reported that they had their diagnosis confirmed by testing. 40 were also diagnosed by a healthcare professional, and we contacted 21 among, those who had consented and validated their responses. So the next question that we wanted to address is whether this rate was different among people with MS and those without MS. So we devised the question in the questionnaires and asking people with participants of this study if they had siblings without MS who were not living with them, and whether they had developed any symptoms suggestive of COVID-19. And that gave us an incidence of 6.2% of COVID-19 among non-MS people, which is similar to our MS group. And also, we found that this incidence rate is not higher than the general population as published by some of the more recent studies, which are also population-based and larger scale. The next question that we wanted to address was what were the factors associated with a higher risk of COVID-19 in people with MS? So we did a multivariable logistic regression analysis. These are all the factors that we included in the analysis, and we took a self-diagnosis of COVID-19 as our primary outcome. We found that taking DMTs does not increase the risk of contracting COVID-19 in people with MS, and if anything, it slightly reduces the risk. We tried different classifications of DMTs. We grouped them based on their efficacy, mechanism of action, and we also took self-injectables out of the equation, and no matter what we tried, we essentially got the same results. We couldn't include individual DMTs in the regression analysis because the numbers in each group were low, but we didn't find a specific DMT to be overrepresented in our COVID-19 groups. And we used different definitions of COVID-19 as well. So the ones that had been confirmed by PCR testing, the ones diagnosed by a clinician, and even COVID-19 based on the WHO criteria. And essentially, we found similar results. This is not unexpected, but we found self-isolation to reduce the risk of contracting COVID-19. We found that an older age does not increase the risk of contracting COVID-19 in people with MS. And then again, if anything, it very slightly reduces the risk. And it seems that people with progressive MS, this is both primary and secondary progressive MS, have a lower risk of contracting COVID-19. However, the reduced risk associated with a higher, an increased age, progressive MS or taking DMTs might be because we were not able to include some of the other confounding factors in the analysis. And we're hoping as we collect more data, we would be able to include those factors that we've captured. The other issue to address is ethnicity. So here we compared Caucasians to non-Caucasians. We didn't find an association between ethnicity and the risk of COVID in the regression analysis. However, a higher proportion of patients with self-diagnosed COVID-19 were non-Caucasian, which is similar to previous reports. We also wanted to look into the association of physical disability and contracting COVID-19. So we included web EDSS and also physical MSIS-29 separately in the analysis. We did not find an association between either of them and the risk of having COVID-19. However, a higher score in physical MSIS predicted a slightly increased risk of COVID-19 when we used the WHO criteria. And it might be because when using the WHO criteria, that defines a more severe form of the disease. So, taking into account the incidence of COVID-19 in our study population and the estimated MS population in the UK, we estimate that around 8,000 people with MS have had COVID-19 in the UK. In this community-based study, the hospitalization rate was 1.3%, whereas in another arm of the COVID-19 and MS study, which is clinician-based, the hospitalization rate was 64%, significantly higher than the community one. And this just confirms what we know about community-based studies, that they sometimes fail to capture more severe forms of disease, and therefore can be useful in complementing findings from clinician and hospital-based studies, since those are biased towards a more severe form of disease. So our study was, these results are from the first couple of months of the UK outbreak of COVID-19, and mostly when people were taking precautionary measures. So we can conclude that when people with MS take precautions, they're not at an increased risk of having COVID-19, and taking DMTs does not appear to increase the risk of contracting the disease at this stage of the pandemic. However, the study is ongoing, and we're actively monitoring the impact of COVID-19 on people with MS as the pandemic evolves. And we're hoping to produce some more results in the future. That's all. Thank you very much for listening.
Thank you very much for this very nice overview of your cohort, and also very reassuring to see that data. Are there questions? I don't see any urgent questions now, so in the interest of time, I would propose we'll move to the next talk, and there'll be time for question in the end. So I'm inviting now Amber Salter, presenting an update on the US and Canadian COViMS registry. Amber, please.
Can you hear me?
Yes.
Okay. Let's see. I just can't get it to be a slideshow, so we'll just leave it like this. Sorry, can't. There we go. Okay, so this is the North American data collection effort. So just an update on some of our numbers. I think most people are familiar with this effort, but it is a for clinician-reported registry collecting de-identified data. So in the database, as of today, we have over 250 cases that have been reported, the majority of which are MS cases. We do have 7 NMO and 3 MOG that have been reported. So the average age in the database of our MS and CIS participants are is about 50. We do have 75%, or a little shy of 75%, are Caucasian. We have 21% that are African American, and 11% that are Hispanic or Latino. And the male gender ratio is pretty consistent, and is about 73% female. I've been trying to add a little bit more in working with the data. So this is just kind of a distribution of the cases that have been reported throughout the US. You can see that we do have a large number of cases from the Northeast in New York, New Jersey, and Massachusetts. And probably some smatterings. There's a big hole in the middle of the country where we don't have a lot of cases reported. The majority of the MS cases are relapsing remitting, 71%. We do have over 20% that are secondary progressive or primary progressive. The majority are taking a disease-modifying therapy, so about 82%, and 80% are laboratory positive cases that have been reported. We do see we have about 31% that have been hospitalized. 16 have had an ICU admission, and we've had 13 deaths. And so just to kind of focus in a little bit on those that have been deceased, the majority of those are male. So 61% of those deceased are male. They are older, and they're almost all white. The one that isn't is actually an unknown race. And the disease duration of those deceased is older. It's mainly progressive disease. You can see mainly non-ambulatory, and 85% have a comorbidity. I think this is pretty consistent with the rest of what the other cohorts are seeing, but we do have almost 50% of those deceased were not on a disease-modifying therapy, and the rest of the ones that are on DMTs are kind of just very sparse in some of the categories. And of those deceased, 5 of those were in the ICU, and 30% were ventilated. And a little bit more on the comorbidities. So the majority of them had hypertension and some with diabetes and other cardiovascular and morbid obesity. And I just recently added in cigarette use. There actually doesn't look to be too much of an association between cigarette use as far as being deceased. The proportions are pretty similar between the two. And that's it.
Thank you very much, Amber, for this summary. Are there questions for Amber? Doesn't look like it. I don't see any in the chat. I think it's very reassuring to see the how the different registries as time evolves actually align, and it really seems that there are no major risk factor associated with certain therapies. Also, we'll still have to see that. Since we are towards the end, I'll come back to the recent paper that was published in Lancet on interferon, and I'll invite Helen, who brought that up, to briefly summarize what they found. Helen, do you want to give us a quick...
Yeah, sorry, I don't have a ton to say, and I've put the link in the chat box if people are interested, and all these articles are freely available. But it's just interesting. It's the editorial is specifically on beta interferon 1b and its use in COVID-19, but it's commenting on a phase 2 open label randomized trial where essentially they had 2 arms and combination of antivirals in both arms, but one arm had beta interferon 1b added to it, and that arm seemed to do better. But obviously there's a lot of issues, you know, it's phase 2, and the upshot is the editorial just comments that more studies are needed to look at the role of beta interferon 1b in the treatment of COVID-19. I hope it doesn't mean that people with MS are going to have a massive rush on beta interferon 1b, so they can't get it if people with MS want it for their treatment, like we saw with hydroxychloroquine and people who needed it to treat their condition. So yeah, no, it's interesting. It's a short read. Recommend you read it.
Thanks a lot, Helen. Are there further questions? If not, then I would propose we close the session. I really thank all of today's speakers. This has been another amazing session, going from the innate immune response over an update from the different registries. Wait, I just quickly see. So there's one more comment that is coming up, a discussion from Margaret Barnett again, is to look back at all patients on interferon and see how they have done. I think this is a good transition for next week's call, and that I'm inviting you all to join. And I think we'll take up that question and invite people to comment on that. With that, I would also actually extend the invitation to another event that is organized by iWiMS this week, and that I would like to invite you, and that is taking place tomorrow or today, depending on where you are located on the continent. It's June 4th. It's at 5 p.m. Central Eastern Time. And it's a leadership session organized by Fiona Costello and Marva Kaiser from our executive committee. And they have invited Dr. Maria Rivas, the current CMO from EMD Serono, to speak on taking new career risks and changing directions. So we hope to see many of you again tomorrow and for sure next week. And I hope you all stay safe. And thanks for joining and see you next week. Bye.